Well, thank you very much for listening to me today. And thank you for introducing me also. I have spent my whole career working on solar cells. I started at Atlantic Richfield when they owned a solar company in 1979. When I just got out of college and thought I'd get a real job after another year or so doing that. But it's been an amazing career working in this business. I'm so happy to see that it is firmly entrenched in the solar and in the energy portfolios around the world. And what I'm here to talk to you today about, most of my career has been spent in R&D, engineering, and operations. The last 15 years have been running factories and worrying about how to reduce cost and how to increase yields and increase performance in high-volume manufacturing. What I'm here to describe to you today is another step down in cost, and it's based on transitioning science and development that was invented here in Ontario. I have colleagues here that actually live here, helped invent this process and bring it to a reality. What I will describe to you today is the work and some of the science and then the commercialization that we're in the midst of doing in all places like in Iceland. So, the company itself is based on producing a different process and making the same result in silicon. Most silicon has been made for the electronics industry, which was adapted to the solar industry. Very high purity, very nice material. I've used an awful lot of it in my career. But it doesn't need to be that expensive or that complex or that capital intense to create materials that are very, very suitable and workable for solar. In the lower right here is a chart of the cost of silicon, or price of silicon in the last several years, where the spike off the chart showed a constraint in supply. There were times when solar silicon or polysilicon was trading and selling for in excess of $250 a kilo, which is just insane. The price now has settled into about the $25, $22 per kilo range. And you can see on the upper graph here, this is just a reference search of number of papers on alternative ways of making silicon. You can see it lagged the price increase by a little bit, but there was an intense interest in looking at ways to make silicon right after this crunch in supply. And you can see some of the folks that have worked on it over the number of years. But it's not a new concept. I would say the thing that's been a challenge is to scale something up that works well, is easy, is simple, and inexpensive. Silicor is a company that has developed this disruptive, low-cost way of making silicon. We'll be producing it at below $9 a kilo cost, and that will compete with about double that price in the traditional means of making silicon. We've proven this by producing over 700 metric tons and 20 million solar cells. The way that was done is, and we're different than some of these other folks that have developed silicon over the years. We have the silicon production and development facility in Vaughan, Ontario, and we have a solar cell making company in Sunnyvale, California. So we would produce the material here in the Toronto area. We would ship it to California, make solar cells, and then we would sell that material to mostly Sharp, frankly. They were using almost all of the cells that we produced in California. What that did was allow us to really optimize the process. And in fact, one of our SPC charts in the factory in both Toronto and in California was the time for data. So we tracked the time from produced silicon to actually getting cell results, and we were averaging about 7.5 to 8 days. And that was important to us because the cycles of learning needed to be fast and they needed to be accurate, and so data collection and data speed was really important to us. The speaker before me said, lots of cycles create lots of learning, right? So we have a strong customer pipeline, which is also a benefit when you're out looking to commercialize something. It's important to know that your product has a home. It's important to know that people want it and that they'll pay for it, right? So I'll show you some charts here in just a minute. As the demand for solar energy continues to rise, we have over a 15% compound annual growth rate. Not many industries, in particular commodity industries, can claim those numbers, so it's challenging the industry to continue to develop ways and materials and things to meet this demand. We consider this ideal market timing to grow this company because Most of the silicon factories around the world are starting to be constrained with this growth, and the traditional means, again, are highly capital intensive, so financing and building new silicon factories is expensive and takes a long time. So we compete well there in that our capex is much lower and we have a shorter build cycle. So we're developing a plant in Iceland, as I mentioned. I'll talk about that in just a second. As I mentioned, this company was born out of two companies. One called 6N Silicon, which again was created and all of the process developed in Vaughan here. It really was born out of the aluminum industry, and when we talk about our process, we make use of the eutectic behavior between silicon and aluminum. It's a very simple process. There's no waste. I'm proud to say for the first time in my career I'm working on a process that I would put next door to my home, frankly. And we do operate in a building with glass front and had some food processing next to us and some building next to us. So it's very safe, very environmentally friendly. As I mentioned, we had a cell company up in California called Cali Solar. We ran that for a number of years while we proved out the process and shipped cells, improved yields, cost, reliability, and then we really went to shipping it to customers through silicon and had them take over the proof, if you will. Previous speakers have shown the dramatic cost reduction in the production of solar cells, modules, and systems. Modules continue to be rapidly cost reduced, and silicon is the biggest component of cost in modules today. If you look at this nice decline in pricing, it's continuing to open up all kinds of geographical markets. This is retail electricity price on the y-axis here, sunlight falling basically equivalent on the x-axis. And everything above the line that makes sense to install solar panels. That competes directly with retail electricity price. Lots of stuff kind of by the line as we continue to reduce costs and reduce price, continue to open up new markets. This is the annual installation projections. This year we're projected to install 57 gigawatts. I've heard numbers as high as the low 60s with some of the demand that's going on. But suffice it to say there's a healthy growth in the industry. The reduction there shown in 2017 is the anticipation of the U.S. tax credit expiring, and there may be a little bit of stalling in the U.S. market at that moment. If you look at the value chain of making solar modules, in the upper banner here, you've got silicon at about 12 cents. Converting that to ingots and wafers sort of doubles. Cells at about the same amount, and then modules, you can see, are, because they're material intensive in frames and glass and EVA junction boxes, add quite a bit of material. But if you look at the single most expensive cost component in the lower right here, as the module costs have come down, systems costs have come down, the red line represents the percentage of the module cost that is silicon alone before you process it, before you really even touch it. So you can see that it's worth working on. It is, again, the single most costly item in the making of a solar module, and the single most costly item if you look at a total installed system. Silicon demand, of course, because solar demand is growing, silicon demand is growing, and this, of course, we pay a lot of attention to. It isn't as rapid for the reasons that were described by the speaker a few talks ago about increases in efficiency, improvements in utilization in grams per watt, but there does need to be more silicon brought to bear there for the industry to continue to grow. As I mentioned, this is one that keeps me up at night, frankly, as I look at the industry growth, because the cost of producing or creating a plant in silicon is not an easy thing to go get funded, frankly. You look at our process by contrast, I mean, in its simplest form, we're melting and solidifying materials. We are running a process where we basically melt silicon and aluminum together in the upper left-hand corner here. We make use of the eutectic behaviors of the two materials. We start at something below 1,000 degrees C, and that's another advantage of the process. We don't consume much energy. We're about 30 to 40% of the traditional means of making silicon and its energy consumption. We slowly cool that mixture down. The silicon solidifies into these flakes. You know, they might be the size of my palm. Those flakes naturally are clean silicon because of the segregation behavior of the silicon itself. So as it's cooling down, the impurities are being forced out of the silicon into the aluminum. They're still very, very low level. The aluminum itself, we like to say we rent the aluminum. I'll show you the process in just a second. But we basically bring the aluminum in, we use it to clean the silicon, and then the aluminum goes out back to the aluminum part we have to have. It's a traded material, it's got a part number, we didn't invent it, we just happen to make it as a byproduct of what we do. So the upper right is a diagram showing basically the idea is for silicon to be cleaned up and segregating the impurities into the molten aluminum as it solidifies. The lower table here is some reference work that has been done in Japan showing you can take pretty dirty metallurgical grade silicon and make very clean silicon through directional solidification, which is really one of the sort of heart and soul of the process that we deploy. There's two parts, as I mentioned. There's sort of melting and making this eutectic, and then there's some directional solidification on the back end of the process. So here's a pictorial of the process itself. We have a large part of our plant we call the foundry. It is the melting of the silicon and the aluminum together. And the metallurgical grade silicon is really what we all start with in making silicon. The polysilicon guys start with it, we start with it. It's a material that is 99.5%, 99.7% clean. And then, of course, we take it to the next level. As I mentioned, the aluminum is temporary in our facility, if you will. It comes in, we use it leaves the facility with a little bit of silicon in it. The aluminum part of it, we're happy about that because that's worth more than the primary aluminum. We're happy because we want solar grade silicon, and we don't really care to make money on the aluminum, but we want it purchased right away, so we basically just kind of loop it through our plant, if you will. And again, this process was born out of the aluminum industry, and I would say it was made real through the work done here in Vaughan, and the motivation is, frankly, because the materials were 10 times what aluminum is worth. Step 2, as I mentioned, what is the result of the process in the mixture and melting and solidifying of these silicon plates is the harvesting of these plates. Now, this is clean silicon, but it happens to be enrobed in aluminum at that point. We harvest these flakes, and then we use, in step 3, dilute HCl and water etch to take the aluminum off of the outside of the flakes. That creates a byproduct called polyaluminum chloride, which is used for water treatment. So we have a byproduct of aluminum that goes back to the aluminum industry. The polyaluminum chloride goes back to large chemical partners that we have out of Europe. And again, for the first time sort of in my career as an engineer, I'm working on something that has no waste. We have 4 materials that come in, we have 3 materials that leave, and basically there's black box on the plant. Everything has value. Step 4, this is where we do a directional solidification. We take these very clean plates that have had the aluminum removed. We spend the rest of the process, we like to say, getting rid of the microscopic level aluminum. So we do 2DS's, directional solidification, where we extract the leftover remains of aluminum, if you will. And then we break it up and ship it to our customers. We did a lot of work at the beginning to try and understand the impurity levels that the solar cells could be tolerant of. And I'll show you the cell results in just a minute. But and we tailored our process, as I mentioned to you, in a way where we would work the recipe in Toronto. We would ship the material, the tonnage, to California, make solar cells, feed back to Toronto, do the analysis, and a very iterative process. Also being backed up, I should mention, by the 11 researchers in Berlin. Some very good work that was done there. Folks that are working on basic material science and the way solar cells behave. Here's some references and specification in the upper left. That specification of silicon is very, very good solar cells, as I'll show you in a minute. And then, again, here's some of the other analysis on SIMS with SIMS and GDMS on resulting and residual materials or impurities in the material. Here are the solar cell results, and what we have here on the very left, in the lots of blue data points, those were the cells that we made in California, the 20 million solar cells that we made. The black line represents industry average for multicrystalline cells. This was pulled out of the market analyst data. Everything that you see to the right of the blue, very dense population, are customer results up to results that we just got a couple of months ago here at 18%. That's what multicrystalline cells are trending towards now in China. Our material performs just like the other material. All we ask folks to do is just substitute it in their plant. That's what they do. They get results that are comparable to what they run with the standard material, if you will, standard in quotes. A lot of the customers that we work with also want to test it against their future cell processes, and that's what you see in the upper data points. Those are future technologies, passivation of surfaces, different kinds of contacts, looking at ways, again, to improve efficiency and to verify if they're going to sign a long-term contract with us for material supply, that they're not inhibited by the bulk performance of the material. And in all cases, the cells produced are exactly the same as what they've gotten with Siemens-grade material. We have strong customer offtake arrangements because of those cell results. So we offer a lower cost product. It's faster to market. We are working with customers to make sure that that it works for them. So it's kind of natural that they would want to buy it. They're going to get it for a lower price. And again, all of this is going to get cost reduction in the solar business to continue to grow the market. Right? So we have customers signed up, and in fact, at this latest point where we're sort of saying we have to slow down a little bit, so you can't build a solar plant. You need to build it, get it running, ship it to the customers that have signed up already, and then if we can expand the plant, we'll certainly take on more. As I mentioned, this process is very environmentally friendly. The lower right picture is our plant in Bonn. It's in a glass-covered building. There is no explosion hazard. There's no issue with emissions. It's a very, very safe process. If you look at how it works, as we discussed, it competes well because both our process and the standard Siemens process start with metallurgical grade silicon. In the Siemens process, it's dissolved in, it's basically broken up, dissolved in acid, turned into a gas, and then resolidified. In our process, as I mentioned and showed you, we're doing some melting and solidification into the next process. So there's no transformation, if you will, thermodynamically. So we save a lot of energy and a lot of cost and a lot of safety concerns by not doing those things. There's no gaseous use in our process. We don't have to use plumbing for the kinds of things that the Siemens guys have to do with silane and various other byproducts that they can do. So we have no waste to landfill. We have a very small footprint comparatively, and again, that results in a lot lower capital cost to deploy. What does that mean when we go out and compete with the big guys? This chart shows the capacity of silicon anticipated in 2018 with everybody's announced additions, and on the y-axis is the total cost. We're going to end up in the $11 a kilo range, competing well with just below $20 in most of the, and this is all in cost of capital, operating costs, etc. With the sort of incumbents being at just below $20, maybe as low as $16.50 for best in class. I think that the real issue here is it's just a simpler process and easy to deploy. You can see by the width of this line, though, that we're going to still be a very, very small portion of the market. By the time this plant is up and running, we'll be about 4% of the industry. We think that positions us well for being sold out. We're introduced a low-cost product, works very well. It's a small portion of the market. We think that's a good way to start. It's a good way to de-risk the project for the large investors. The project itself is going to be about $850 million, so it's been quite a journey getting that money raised, I will tell you. From a capital standpoint, our plant in Iceland will be less than half of what the most recent plants in China are being built. So again, what this means for investors is lower investment and faster time to pay back. Why are we in Iceland? I will tell you one of the most important reasons we're in Iceland is there has been a trade war between the U.S. and China on solar goods. That started about the time we were ready to locate this plant in the state of Mississippi. We realized very quickly that that was going to get passed and that we needed to, and then China retaliated by putting a large tariff on any silicon made in the United States, 60%. In certain cases, even more. So all of our cost advantages go away by building this plant in the United States currently. And a lot of the investors basically didn't want to, take the risk in case that did come to pass. Well, it did come to pass. All of our customers are in China because you saw that all of the models virtually are made in China and Taiwan. So we need to be able to ship this material tariff-free. Iceland signed a 50-year trade agreement on all goods and services for China. That was not something we knew when we first looked at Iceland. Super friendly business environment, low cost power, it's all renewable power, geothermal and hydro. I got to visit my first geothermal plant. Oh my gosh, there was a single person in it. It's really amazing. We have availability of local supply. There's a very large metals infrastructure in Iceland, aluminum, and they are putting 3 metallurgical grade silicon plants in, which are not for us, but just happen to be coincident with our locating of our plant. Eventually, we will be an all-Icelandic material converter, I think. Why do they like us, or why are we valuable? And we're obviously very green. We're bringing solar to Iceland, which is a difficult place to imagine putting a lot of solar panels in. We're creating 450 very high-paying, good jobs, long-term jobs. We're complementary to the aluminum industry. As I mentioned, they're building metallurgical grade silicon factories there. And they have a very strong leadership position in environmental concerns. I think it's been amazing to be able to come to like that. It's so progressive. After having been there, it's not the number of times that I've been there, I'm happy that they're worried about the environment because they have something to worry about. It's so beautiful. The plant is about 40 minutes north of Reykjavik in a harbor or a fjord that was used during World War II to hide subs. Kind of an interesting history there. We're next to an aluminum plant and an alkaline ferrosilicon plant. We share a harbor with those plants. We will be shipping materials by ship and sharing the harbor fees and such and dock holders with those plants. That map is a little bit faint, but we have growth plans, of course, being a small part of the industry, and as this works out and we get the first plant built and running, we expect that there will continue to be demand for this. We have looked at a number of places in the United States. We mentioned Mississippi. We spent a really good bit of time in Quebec. I think it's been a fabulous fit for us to go to Quebec for our next plant. Iceland, where we are now, in Norway is a good fit for all the same reasons as Quebec and Iceland are. We even went to Saudi Arabia to look at locating this plant because they have a large metals industry there and a large solar program. I think it would have just taken a long time to get that solidified and done. But suffice it to say that Iceland is the first of what we hope to be many. It's a commodity now. I think we're just a piece of the solar business, if you will, and the cost reduction opportunities that exist still in the value chain. And that's a picture of us harvesting twigs in our plants. Just to give you an idea of the industrial nature. This is in Vaughan, and what we're doing there is the molten aluminum has been poured off, and these are the silicon flakes that reside in a large mold. We're building tons of this. I like to say I exchanged my white lab coat for I wear an aluminum suit now in the plant, as my colleagues do too. It's a very industrial process, very inexpensive, very hardy, just the kind of thing you want for low cost and getting things done. So thank you for your attention, and I appreciate the interest that you're having over there.
Okay, thank you very much. We have time for a few questions.
I am responsible for the collection of socio-economic indicators. You've seen some of that. I presented that my presentation, and I need to report this to the IETS on behalf of Canada. I was wondering if you would mind sharing with us the approximate level of production you have seen in 2014?
In 2014, we're just doing experimentation models. One of the things about running a small plant, and as the price dropped, we are not able to make money in the small plant that we run now. The scale is what's going to give us the ability to do that. So we're just doing demonstrations and small scale experimentation. Fair enough?
You mentioned the plant size.
Oh, Iceland is 16,000 metric tons.
And in Canada, just because we mentioned that we produce 700 megatons of silicon so far, so that translates to how much per year?
Oh, that was in about a year. That was, we sold most of that to Chinese firms like that.
And that was produced in how many years? 700 megatons?
About a year.
About a
Year and a half.
And that corresponds to your current level of production?
We're not running that right now because, again, the price of selling silicon is about $25 in our costs in our small plant. Not only because of it being small, but price of electricity is high there, et cetera, et cetera. We'd be taking lots of money on every equivalent to shift, so not a good business plan.
I have a question. As I understood that your aluminum cleaning process removes all the metal, more or less. But what about phosphorus and chlorine?
I'm going to let Al answer that.
Yeah, exactly.
You want me to go back to the
specifications of Yes, I saw the specifications, but the question is that the primary phosphorus and the chlorine which is in the silicon, or whether you have an additional step to clean it out? I mean, it was sufficient for the solar cell, that's my understanding. Yes. The remaining part, but do you have any specific process to clean it up with respect to phosphorus and chlorine?
No, not specific. We have directional simplification at the end of the process. Of course, we use a little bit of phosphorus, but we don't do that.
Maybe that's why there's iron at 0.05 ppm. How's that compare to competitors or Disruptive?
I think it's fairly measurable. It's barely detected in the same class. We don't really have any other large competitors right now. It's FDR. So, you know, they're both done where you put in your gases, fine, and solidify. Yeah, barely measurable in competitive class.
We have time for another question, if there were one. Okay, so please don't go anywhere, and let's thank Terry again for a very nice talk.